All right, so in this section of notes, we look at solubility, and we specifically look at the factors that affect the solubility. Now, we're going to concentrate a lot of our information on this common ion and the common ion effect. And we've seen that with calculations of our pH and our titrations. But there's some things that we'll also mention that the pH of a specific solution can affect the solubility, along with these items called complexing agents we'll briefly mention. And then at the very end of these notes, we'll talk about amphoterrorism here. Okay, so all of these things that affect this, we're going to factor in our focus on our particular common ion. Okay, so our common ion effect, we're going to start with a definition here, and it's the solubility is actually going to decrease when we add a common ion to our particular solution. Okay, so remember, with KSP or solubility, we would have an equilibrium that is set up in this particular nature. Okay, now the bottom bullet there says if F minus fluoride ions are added by the addition of some fluoride ion compound. So for example, sodium fluoride, the equilibrium is going to shift. So just as a reminder, with equilibrium, if we add more of this, I'm just going to highlight and say simply add more. The equilibrium, based on Le Chatelier's principle, is going to shift to the opposite side in which we add it. So we add more of this fluoride, and the equilibrium is going to shift back left, which means more calcium fluoride is going to be present, and it's going to be present in that solid form. So your solubility is actually going to decrease. Okay, so last thing I want to put here is our equilibrium shift follows this specific arrow. Okay, so equilibrium, Le Chatelier's principle, give us a really simple picture. What we want to do now is we actually want to identify specific numerical values that can affect that. Okay, so let's go through. We'll actually do a couple examples, and they're related to each other, so we'll get to use quite a bit of information here. The first one here is if we want to know the molar solubility, KSP, of calcium fluoride. Okay, now calcium fluoride, we're actually going to start with this, and it's the same equilibrium that we saw from our previous equation. Okay, so or the previous slide, we have our calcium fluoride. Okay, so we have CaF2, and this is a solid. Okay, now remember, we have our equilibrium arrows, and calcium fluoride would break down into calcium 2 plus, and it's dissolved in water, so we have that as aqueous, and we have, this is really important, 2F minus. Okay, now what I always like to do with this or with any equilibrium expression is build our equilibrium expression from our equation. Okay, so remember, I'm going to write this in green and above it, that our KSP, SP for solubility, is going to be equal to the concentration of our particular calcium times the concentration of our fluoride. Hello? Okay. All right, appreciate it. Thank you. Times our fluoride ion, but there is something that we need to factor in, and that is this 2 to represent a squared power. Okay, remember, we go back to our information on our equilibrium. Now, technically, that would be divided by 1 because calcium fluoride as a solid is a pure substance, but we don't need to write that. Okay, The other bit of information is this. Remember, our big charts say what our particular KSP is. All right, so these are known values at 25 degrees Celsius. And the KSP of our calcium fluoride is 3.9 times 10 to the negative 11. Okay, so the actual known value of KSP, and it's found in our chart here, is 3.9 times 10 to the negative 11. And remember, K has no unit. All right, so there's all the basic information. All right, now to solve solubility problems, we do need to set up our particular ice chart. All right, so I'm going to go ahead and I'm going to label our ice chart. Now, it doesn't really matter our calcium fluoride because it's a solid. It's not going to factor into our KSP value of calculation. But then we need to think about what we have to start with and what common ion we have. Okay, so I'm going to just box in where it says number 1, we start in a solution of 0.01 molar calcium nitrate. Okay, I'm going to write this above here, right next to our start of our problem. But calcium nitrate, if it's in solution here, is going to break into this. It is going to break into calcium, and it is going to break into 2 of these nitrate ions. Okay, now technically both of these would be AQ for aqueous solutions. And then we can talk about how much calcium we have. Well, check this out. If we start out with 0.010 molar, and calcium nitrate and calcium both have a 1-to-1 mole ratio, we could say that we automatically have 0.010 molar calcium. Now, technically, we'd have 0.02 molar nitrate, but we don't need to worry about that, right? It's a spectating ion, okay? This is our important part here. Initially, we have a value of 0.010 molar of our calcium. We do not have any initial value of our particular fluoride. All right. Now, remember with this, both of these things are going to gain. Both of these things are going to gain a unknown value, and so they're going to gain some amount X, and they're going to gain some amount X. All right. So now at equilibrium, and this is our important part here, is this. We have 0.010 molar plus X. We have X, and there's a major mistake here. I totally forgot about the coefficient of 2. This is technically 2X. Technically 2X there. All right. So make sure you factor in your particular coefficients. All right. Didn't have to worry about that with calcium because it's just a coefficient of 1. All right. Now we can plug these particular numbers back into our KSP that we established from up top. So remember, KSP is equal to 3.9 times 10 to the negative 11. And so we would say, all right, we have 3.9 times 10 to the negative 11th. And this is equal to calcium concentration, which is going to be our particular 0.010 plus X times, and this is really important that we follow our KSP we established from above, times 2X squared. Okay, now I'm going to go ahead and I'm going to consolidate this, and we would get this. Number 1, this plus X is going to be so small that we can say this. We can say that our assumption works, just like we've seen with our acid and bases problems before. So assumption works. You could test that. Remember, KSP times 100 should be much smaller than your original concentration. So if that works, we could factor out that X. And in fact, I'm going to go ahead and do that. Okay, so assumption works. We can take away that particular X. And so we are left with this. Okay, now what I'll do here is I'll consolidate our particular equation, and we will get to this. So I'm going to take 2x squared, which become 4x squared. And so then I'll take 4 times 0.01, and I would end up with 0.04. So when I consolidate this, I would end up with 3.9 times 10 to the negative 11th equals 0.04 x squared. Okay, now we would divide each side by 0.04. Okay, we would divide by each side by 0.04. And when we do that, we take 3.9 times 10 to the negative 11th, and we would divide by 0.04. So 3.9 times 10 to the negative 11th divided by 0.04 would get us a value of 9.75 times 10 to the negative 10th equals, we can't forget about this x squared, that's really important. We would take the square root of both sides. So I take the square root of my answer I just acquired there, and I get a molar solubility here by the time I round to 2 significant digits of 3.1 times 10 to the negative 5th equals X, which, remember, the way in which we write our molar solubility is in the terms of our particular moles per liters, or simply molarity. Okay, so our molar solubility here would be 3.1 times 10 to the negative 5th, big capital M. All right. Now, I'm going to take a lot of information here, and I'm going to use it on our next problem here. Okay, so I'm actually going to copy and paste a lot of this info here. That way we don't have to rewrite it, and we can start very quickly and very similar to where we began our last problem here. And we can pick up right from here. Now, there's going to be a few differences, okay? But we're still going to use our same type of concept here, all right? Again, solubility is going to decrease here because we have a common ion, right? So now we're going to do another problem, very similar. We still have calcium fluoride. That's why I copied and pasted that last stuff. But now we have 0.01 molar sodium fluoride, all right? And that's a big factor here, all right? So I'm going to go ahead and I am going to paste that info that we had to start out with, and I'm going to move it, set it in some position here like this. And again, we have some different starting information here. And so this stuff in blue, I'm going to go ahead and eliminate for right now. Okay, but we start out exactly the same. The difference now is we have a different common ion. Okay, so our different common ion here is now going to be our particular 0.01 molar sodium fluoride. Okay, now sodium fluoride, NaF, right? It would break down to sodium ions, Na with a 1+, okay, and it's dissolved in water, so aqueous, and it would break down into our fluoride, our F minus, okay? Now, again, we are going to have this, right? If we started out with 0.010 molar sodium fluoride, this is all 1-to-1. Our item of interest, or our ion of interest, would be fluoride, which would be 0.010 molar because they're 1-to-1. So our initial amount for our fluoride would be 0.010 molar. Okay. Now, remember, we would actually gain plus 2x. And so at equilibrium for fluoride, we would have this. We'd have 0.010 molar plus 2x. And over here, remember, there's no mention of calcium this time, so we wouldn't have any calcium. We would gain some unknown amount, and then we would have at our equilibrium that x, that factor we don't know yet. Okay, what we can do is this. Again, our assumption is going to work. Our assumption is going to work, and so KSP times 100 is significantly smaller than our original concentration, which is given at 0.01. So we can say, yep, the assumption works, which means this plus 2x is so small that it's really not going to change that 0.01. So we could cross it out. And so truly for us, what we would put here is just simply 0.010 molar. Okay. Now, the way the KSP is set up, this is going to change some things here. Okay. So we're going to solve for our KSP and see what happens. All right. KSP is still that 3.9 times 10 to the negative 11th. And this is equal to our X, which we had for calcium. Okay. So our X that we had for calcium, and it is equal to our 0.01 after we went through our assumption. But we have to do one really important thing that we cannot forget. And that is to square this, because that's exactly what our particular solubility expression says to do. Okay, so now when we square this, this is going to affect our calculation. It's going to affect our value and ultimately affect our solubility. Okay, so when we do this, what happens is this. We get 3.9 times 10 to the negative 11th. And we are going to divide this by 0.010 squared. So on each side, I'm going to divide it by 0.010 squared, and we will see what we get here. Okay, so we divide each side by this 0.010 squared, and we get this. We get a value, our X, to be 3.9 times 10 to the negative 7th big M. All right. Now, before, with just that calcium, that 0.01 molar of initial calcium, we had a value of 3.1 times 10 to the negative 5th. That is bigger than this number, which makes sense, right? That squaring factor is a significant difference and a significant change in our solubility or effect of our solubility. All right. So a little bit more in-depth analysis here on solubility. We'll now go through some other factors without doing some specific problems. All right. So solubility and pH. All right. So it depends what kind of pH we have, whether it's acidic or basic, how that's going to affect our solubility. So it says a solubility of a slightly soluble salt is actually going to increase as pH decreases. And you have to remember, it depends what substance is actually being dissolved, what solid substance is being dissolved. That's going to determine how much our particular pH is going to affect that solubility. Okay. I give two examples here. I'm really not too worried about going over these in depth, but again, magnesium hydroxide, that's definitely a strong base, okay? And so as your pH decreases right here, your amount of H plus increases. And so what that means is as the pH is going to decrease, you're going to be more acidic, more H plus is going to be involved, which means more of that base can be dissolved. Okay, so your solubility actually increases. We can dissolve more in a lower pH. Now, lead 2 fluoride, okay, as you add a strong acid, the pH decreases, H plus increases, and your solubility also increases. A very similar type of factor, a little bit different chemistry happening there, but that's what occurs. Okay, complex ions. We haven't really talked a whole lot about complex ions. Essentially, you can think about this as a compound with a type of charge. Well, depending on that complex ion is going to affect how much your particular solid can be dissolved. And so you can see with our solubility of silver chloride, it is actually going to be difference, and it's going to actually increase the solid or solubility as we have that specific Lewis base. Okay, again, getting a little bit more complicated with those complex ions. And then we talk about this with amphotericin. So first off, what is amphotericin? It's a substance that can act as an acid or a base, and depending on what it's dissolved in or what the compound is actually paired with, the ion's actually paired with, is actually going to determine, hey, is this going to act as an acid or a base, right? So we have several examples of different ions: aluminum, chromium, zinc, and tin. And as this dissolves in a strong acid or a strong base, it's going to affect everything that we've talked about in terms of solubility. Okay, so our last three factors were factors that are a lot more detailed in the solubility. There's a lot more you could talk about with solubility. The focus there is on those problems. Again, as you have a common ion, your solubility is going to be affected, and it's going to be affected pretty greatly, as we saw with those two problems that we did in this specific set of notes.